Hello everyone. Today we'll be discussing about one of the applications or say where microcanonical ensemble will be applied. That is a one-dimensional simple harmonic oscillator. So let us quickly go to that. We know Hamiltonian will be given by half kq square plus p square by 2m. Again, this will be the expressions, that is q is equal to a cos omega t plus phi and p is equal to m q dot, which will be equal to minus m omega sin omega t plus phi. We are assuming that you know the basics of a simple harmonic oscillator, where omega is the angular frequency of vibration, as the amplitude omega is equal to root k by m, and we know again energy is equal to half k a square. So the total energy is equal to half k a square, which is equal to half m omega square a square, which is a constant of motion. Moving further, we know the energy we will be taking is constant. So this energy expression, that is half kq square plus p square by 2m is equal to E, can be written in the form of an ellipse. Let us this will be written as q square by root of 2e by m omega square plus p square by root 2me whole square is equal to 1. You know what is the equation of an ellipse? X square plus a square by y square by b square. So again, the area of an ellipse is equal to pi ab. So which will be pi root 2me into root of 2e by m omega square, which is 2 pi e by omega. So this is the actually the area of the ellipse. Now in this case, we are restricting the oscillator energies in the interval e raised to plus delta by 2 to e raised to minus delta by 2. And you know why is it so? Because we are talking about a microcanonical ensemble. So the volume of the relevant region will be the difference between these two. So again, we know the total area is this much. So here the total volume of the relevant space will be 2 pi e plus delta by 2 by omega minus 2 pi e minus delta by 2 by omega. So here you get 2 pi delta by omega. That is the volume of the relevant region. So from our knowledge of quantum mechanics, the energy eigenvalues of harmonic oscillator is given by En is equal to n plus half h cross omega, where n is equal to 0, 1, 2. Now when you take the different values of n, you will realize that between them the energy, the spacing is h cross omega. So with that knowledge, let us say in a width of n delta energy, there will be delta by h cross omega levels. That means the number of microstates, omega is given by delta by h cross omega. We have in the beginning itself we have discussed that gamma is equal to omega by omega naught. It is the relevant region in the phase space divided by the volume occupied by one microstate. That will be the number of microstates, which is gamma. Again, let me tell you, we have done a detailed explicit calculation of microstates, and we have realized that gamma is the expression for that. And we have derived this one also in the previous classes. So now apply omega and gamma, that is the relevant region. The relevant region is given by 2 pi delta by omega, the relevant region in the phase space. And then delta by h cross omega is the number of microstates possible. So therefore omega naught is equal to 2 pi h bar. We know h bar is h by 2 pi, so this will be h. Again, that itself means that the for 1 degree of freedom, this will be given by h. For an n-harmonic oscillator, this will be hn. And that's it. That is what we have discussed in the previous classes, and we have proved also. And same thing, we are again getting it in one-dimensional harmonic oscillator also. So that's it. Thank you.